Hello, and welcome to this Chemistry 105 review video. Today, I will be reviewing 4.3 through 4.4 chemical names and formulas. One of the most daunting parts about being a chemistry student is naming. A lot of students go into chemistry, learn about a lot of compounds, and get really confused about naming. The first question that a lot of these students ask is why? Why do we have these rules that seem arbitrary and seem to complicate and make things harder? And you can thank this group, the International Union of Pure and Applied Chemistry, or IUPAC, for these kind of daunting rules, but they do serve a really important purpose. The goal of IUPAC was to standardize the naming of molecules because it's important to be able to communicate the information of a molecule when talking about one. So they came up with really clever and very specific rules to kind of convert in your mind the name of a compound and the molecule, the actual formula. So you might be asking yourself, why isn't the technical name for vanilla vanillacillin? Well, what does vanillacillin mean to you as a chemist? It doesn't help you. So that's kind of why we communicate with these rules. So before we get into any of the rules, you want to memorize these prefixes. I'm sure you've seen this in your math classes. Here are the first 10, and these will be really important in naming compounds. So before we get into the actual rules, let's look at the periodic table. If you recall, we have 13 cation groups. 3 of those which are main group cation groups, and the other 10 which are transitional metal cation groups. Now, what makes these main group cation groups is that they have a consistent charge, positive charge, while these transitional ones are, they kind of go back and forth. All right. And as you can also remember, we have 4 anion groups. They are all in the main group, and they are consistently they have a consistent charges. So before we get into naming compounds, let's talk about naming first a single pure cation and a single pure anion. All right, so let's start with cations. So, like I said, there's 2 different types of cations. There's a main group cations and transitional cations, and they each have similar but a little bit different rules. So main group cations, because their charge is consistent, we go with this pretty simple rule. The name of the cation and the word ion. So here we have a sodium with a consistent +1 charge. This one will be just, you guessed it, it's pretty straightforward, a sodium ion. All right, next one, we have strontium, which is also a main group cation. And that has a consistent charge of 2+. And this one, following the same rule, will be strontium ion. All right, now a little bit different, we have the transition cations. Because these cations aren't consistent in their charge, we need to clarify that when we name them. So the chemists that you're talking to know what charge iron you have, for example. So speaking of iron, our first example, we have an iron with a 2+ charge. And so we'll call it iron 2 ion. Next, we have another transitional cation, chromium, with a 4+ charge. That'll be chromium 4 ion. All right, awesome. And this is pretty straightforward. Once you've gotten cations, anions won't be very different. All right, so anions, the groups 14 through 17 that have consistent negative charges go by this rule. You'll say the base of the element and add "ide" to the end. So what is meant by base is usually the first half of the name of the element. So for example, silicon will be silicide. Oxygen will be oxide. Chlorine will be chloride. All right, awesome. So once you know these basic rules about cations and anions, from here it's really just building. So it's building upon this and the prefixes that you should have memorized. All right, so let's move into acids. There are 2 different types of acids, and what makes an acid is when you add a hydrogen to it. Our first, more simpler acid is called a binary acid. So one thing to note about binary acids is that it only constitutes as a binary acid if it's a hydrogen plus an element from the halogen group. And if you recall, the halogen group is this group 17. Everything in this group is a halogen. All right, so if we go through this example, we have a hydrogen and a fluorine. Fluorine is a halogen. We go by this rule shown up here. It'll be hydro, the base of that element, ic, and the word acid. So this one will be hydrofluoric acid. Also pretty straightforward. Okay, you have binary acids. Now oxoacids are a little bit different because they usually involve polyatomic ions, which I'll get to in a second. So polyatomic ions usually have a defined name to them. And what makes an oxoacid is that you combine a hydrogen or hydrogens with some oxoanion, which means your anion, which is usually polyatomic, has oxygen inside of it somewhere. So let's look through the instructions, some of the rules for oxoacids. So if your oxoanion ends in "ite", then your acid becomes "us" plus the word acid. If your oxoanion ends in "ate", your acid ends in "ic" with the word acid. So here I have some examples. We have nitrite, ends in "ite". We have nitrate, ends in "ate". So let's say we add a hydrogen. We add a hydrogen to nitrite, making it an acid. So then, following this rule, nitrite becomes nitrous acid. And nitrate, following these rules, becomes nitric acid. Now, it's important, again, driving this home to recognize that it's an oxo acid when it has an oxygen, hydrogen is being added to it, and added to an anion with oxygen. All right, so that is acids. And one more thing before I get into the general naming, hydrated salts. So hydrated salts come from, what makes a hydrated salt is when you have some metal salt that combines with water. And kind of what happens is that the water is kind of embedded in the salt. And we have a name for them. So the name for a hydrated salt is, first, you'll say the regular compound name without the, as if what it would be called without the water part. And then you'll use your prefix, so how many waters there are, and then hydrate. Okay, so let's do this example. This is copper sulfate. So this, like I said, the first part will just be the compound name, so copper sulfate. And then it'll be the prefix, the Greek prefix, and if we remember, 5 is penta. So this will be called copper sulfate pentoxide. Now, one thing to note that I didn't bring up is when your prefix ends in a vowel and your element starts in a vowel, sorry, not pentoxide, pentahydrate. But one thing I should mention, if you did have 5 oxygens, for example, instead of pentaoxide, it would be pentoxide, just because that diphthong is kind of excessive. All right, so now that we've got cations, anions, acids, and hydrated salts, I want to move on to this really helpful nomenclature flowchart that helps me memorize the names of compounds. So before we go through this chart, something else that's really important to memorize are these diatomic elements. So what it means by what diatomic element means is that usually in nature it exists together. So oxygen doesn't usually exist by itself. It usually exists as 2 of them together, so O2. And this is a really great acronym, Brinkelhoff. All right, so this chart kind of goes through the ionic compounds, so a cation and an anion. It'll utilize polyatomic ions, and you'll also get some covalent compounds in here. So a really good way to memorize this flowchart, what's helped me, is just doing a bunch of practice problems on it. So let's go through some together. Let's start off with a pretty easy one. N2O5. So we have 2 nitrogens and 5 oxygens. And all we really have to do with this is ask ourselves a few questions. Okay, first question. Does the compound contain more than 2 elements? N2O5 only contains 2. So that's a no. Let's go to no. Next question. Is the compound ionic? Does it contain a metal or covalent? N2O5 is covalent. It does not contain a metal. So we'll go this way. Now let's read the instructions here. Use Greek prefixes to indicate how many of each atom is present, according to the pattern. Prefix, element, ide. Easy enough. Okay, so our first element is nitrogen. We have 2 of them. And as we see here, the prefix for 2 is di, and then the element name, so dinitrogen. The prefix for 5 is penta, and again, we're not going to say pentaoxide, we're going to say pentoxide. And, well, I've said it already, but it'll end, it's the base of the element, and then it'll end in ide, because it's an anion. All right, awesome, easy enough. Okay, next one. FeCl3. Now, like I said before, we don't know the charge of iron. But just based off this formula, we can find the charge, and it is really important to clarify that in the name, in this compound. All right, so FeCl3, let's go through this chart. Does the compound contain more than 2 elements? No, so we'll go this way. Is the compound ionic or covalent? It is ionic, so we'll go this way. Does the compound contain a transition metal? Yes, Fe, if you recall, is a transition metal. Okay, so we'll go this way. Okay, the instructions say, determine the charge on the cation from the charge on the anion. Then name both ions, including a Roman numeral. So thinking back to the rules of the cation, it's really similar, except now we don't know the charge. I mean, doesn't look like it, at least. This doesn't exactly tell us what the charge of iron, but with a little bit more inspection, you can figure this out. So if you recall, when making these subscripts for a compound, each element in a compound, you're going to kind of have to cross the charges to the subscript. So for example, chlorine has a very definite, consistent charge of -1. And so if we cross that to the subscript of iron, it is going to be 1, but we're not going to write 1. And so you kind of can see where I'm going with this. Since this is a 3, this comes from the charge of iron, which is 3+. That's going to be 3+. So iron has a charge of 3+. Good to know. So it says determine the charge on the cation from the charge on the anion. Awesome, we did that. 3. Then name both ions, including a Roman numeral. Okay, so we have iron, and then Roman numeral 3. And then again, since chlorine is an anion, it'll be chloride. So it'll be iron 3 chloride. Awesome. Now, last example, we have Ca3PO4 2, or calcium, 3 calciums, and 2 phosphates. Okay, let's go through this flowchart. Does the compound contain more than 2 elements? Yes, contains 3. Does the compound contain a transition metal? No. The instructions say, name both ions. Pretty easy, right? If necessary, consult the polyatomic ions list. Now, like I said, this is phosphate. PO4 is phosphate. So it just says, name both ions. Easy. Calcium, phosphate. Perfect. Now, as you've probably seen already, I've brought up polyatomic ions a lot during this review. And that is because they are so important in naming compounds. Here are just a few of the most common important polyatomic ions that you'll see in an intro chemistry class. What makes them, so basically what a polyatomic ion is it's a compound that has a charge, as you can see here. So the trick with memorizing these is there really is no trick. It's really just practicing what I've kind of said before. The more that you use these polyatomic ions, naming them, drawing Lewis structures for them, etc., the faster you memorize them. It does seem kind of like a lot, but a lot of them have the same kind of rules. Like, for example, nitrite there's 2 oxygens, and chlorite has 2 oxygens. So a lot of them are pretty straightforward in how they're named. So yeah, that is the end of the review. I hope you learned a little bit about naming compounds. Thank you.